Okay, all right, Math 182 students. We are now in section 8.3. We talked in the last couple classes about series, and we looked at different kinds of series, and you've experienced them in your homework. Geometric series, harmonic series, telescoping series, even power series. These are all very common types of series, and they're important for our calculus understanding. In section 8.3, we look at some new kinds of series that are usually a little more difficult than the series you saw in section 8.2, because, like, for instance, in our last class, we did, for this problem, we did the question A. Okay, does that series converge or diverge? And this series here, we determined converged, and we used what's called the comparison test to compare that series to an easier series called a p-series. Well, I'm going to do a similar problem in part B. So I removed the problem that I had, and I want to do the B problem. So in your notes, change B to the series from n equals 1 to infinity of 1 divided by the square root of n squared plus 4. And what I'm going to do is I'm actually going to go to the whiteboard to work this problem. We want to know if that series converges or diverges. Okay, and actually I think I want to do one more thing. Instead of n squared, let's make it n to the third power. Okay, so it's n to the third power plus 4 under the square root sign. Okay. All right, so let's go ahead and move to the whiteboard, and I'll work this problem out. We want to know if that series converges or diverges. Okay, so here we go to the whiteboard, and let me change my font. Okay, one moment here. One moment, everybody. I think I'm going to even do one more thing. No, this is fine. This is fine. Let's just work it out here. So, all right. So here's our series. All right, and what we need to do here is we want to try to make a comparison. We want to make a comparison for this particular series. What's making this difficult, this series, to analyze? You know, we want to know if that's right, the square root, and Yonatan notes, that's right, Claire, and Yonatan notes the plus 4. So I want to know if that series converges. Okay, I want to know if that series converges. So one thing we learned is that if you have this series here, okay, this is a p-series. And the n doesn't have to start at 1. It could start at n equals 10. It doesn't matter the starting value of n. Okay, if your series is of the form 1 over n to the p power, it's called a p-series. And the p-series converges. P-series converges. Well, p does not have to be an integer, Yonatan. P does not have to be an integer. That's right. So the P series converges if P is greater than what value?
1.
1. That's right. Good. Good. Okay. So what we're going to do here, and this is a fact that we're going to use. We're going to use this fact to help us. Okay, so given that, we're going to use the comparison test. We're going to use the comparison test. So, all right, I'm going to take 1 over the square root of n cubed plus 4. Okay, I'm going to take that, and I'm going to say that that term. So this is like in the series here. This is your term, right? This is your term of the series. This is the a sub n. So this is your a sub n term. And I want to set that less than or equal to a term b sub n. And I got to figure out what b sub n is going to be. The 1 I'm going to leave upstairs. The bottom, I'm going to leave the square root there. And what can I put under the square root? That's easier than n cubed plus 4. Yeah, that's right. Good, Yonatan. N cubed. Okay, so by the comparison test, well, and that will equal 1 over n cubed raised to the half power, and that's going to equal 1 over n to the 3/2 power. So let's see here. We have the series 1 over n to the 3/2 power. Let me try to make that a little bit nicer. Naturally, this goes in your notes. What does this series do? Converge or diverge? What does this series from n equals 1 to infinity of 1 over n to the 3/2 do? It converges.
Converge.
That's right, Yonatan. That's right, Clay. It converges. Why? Because it is a P series with P equal to what value? What's P equal to?
1.5.
1.5 or 3/2. Okay.
Yep.
And that's greater than 1. That's all you need to say. That proves, I mean, they prove this result here in the textbook. But for our purposes, like for our homework, for our exams, showing our work, we can just say, hey, that's a P series which converges because P equals 3/2, which is greater than 1. Okay. Yes, Mohammed, but we're not done yet, of course, with it. But yes, Mohammed? All right, well, let's look at this series here. This is the series that we're interested in. Uh, well, here's what we're doing, Susanna. Here's what we're doing. Let me just let me ask you this. This is the series that we're interested in, right? This
Yes.
series here, the second series, we know something about that series. This series here, we don't know what that series does. However, and let me get that square root that over there a little bit. Which is true? Is the first series less than the second series, or is the first series greater than the second series? Which is true? Is the first series less than the second series or greater than the second series? By virtue
Less.
of this inequality here. Now I know more than Yonatan knows that answer. Is the first series, is this series here, it would, if it were, if it would its sum, whatever it is, would its sum be smaller than the second series or greater than the second series? The series n equals 1 to infinity of 1 over the square root of n cubed. Here's series 1. Here's series 2. Which series has bigger terms?
Shouldn't
Series 1 or series 2?
shouldn't series 1 should have bigger terms since we have +4?
Well, but look here. Look at your comparison. Look at your comparison here. Hold that thought. Isn't 1 divided by the square root of n cubed plus 4 less than 1 over the square root of n cubed? I mean, Yonatan's noting this, the denominator here, square root of n cubed plus 4, is greater than the denominator of the square root of n cubed. So the a sub n term has to be less than the b sub n term. You see that? N cubed plus 4 is greater than n cubed, but you have n cubed plus 4 in the denominator. So that's going to make the a sub n term smaller than the b sub n term. And therefore, the series that we're interested in, which is the series where we have the term 1 over the square root of n cubed plus 4, that series has to be less than the p series, right? I want to make sure, I want to make sure everybody's comfortable with this. Is this okay? Less than. Okay, Suzanne is comfortable. Give me a thumbs up if you're comfortable. Give me a thumbs up if you're comfortable. Okay, Victoria is good. Masume, Clea. All right. Franklin's good. All right. Niat, how about you? Are you okay? All right. Zaina, how about you? Niat, you're good. Thank you, Niat. All right. Well, then look what happens here. This P series converges. This converges. Means the sum is finite. Sum is finite. It's not infinity. if the bigger series converges, this implies then that this series converges too. The series that we care about, that converges also. Its sum will also be finite. It'll be smaller. Has to be. And that's one way to use the comparison test. Okay, so our series converges. Yes, it does. Susanna?
You'll probably get to this, but if it was bigger, would we not be able to assume it converges?
That's right. If the let me see here. One moment. Correct. That's correct. If the series we're interested in, if the series that we were interested in, or the series that we are interested in, is bigger than a convergence series, you can't say anything. You can't tell, and that means in that case you have to use another type of test. And actually, that's a great question, because it's going to lead us into our next example. All right. Clea, good question, Susanna. Clea, good question.
Yeah, so I just wanted to ask, in this type of problem when we do the comparison test in like exam, like in the web assign, we don't have to find a sum. We just write, since the p is bigger than 1, then it converges.
That's correct. So a lot of the problems in section 8.3, which I've deactivated for now because I don't want, a lot of the problems are multiple choice, and you got one try to get the answer right, converge or diverge. And on the exam, there'll be some problems like that too,
Yes.
right? The fourth exam. So they don't necessarily want you to find the sum or estimate the sum, but there is a way to estimate the sum. I'll show you that a little later in class. But right, for certainly some of the problems, it's just, does the series converge or diverge? And you have to be very careful before you answer it. That's right. Good question. Good question. Let me see here. So let me bring this back here. Let's look at a few more problems. And you notice, by the way, this series, the terms of the series are all positive. So in section 8.3, we're dealing with series for, I want to be a little careful how I phrase that. Yeah, the terms of the series are basically positive. If you have a series where the terms of the series are, some are positive and some are negative, then that's like a different situation. And we'll deal with that when we get to section 8.4. But let's go ahead and look at another couple of examples here. Okay, so let me give you a moment to copy these examples down. Okay, so let's take a look now at this problem here. So we have, let's look at series A. Series A, and one moment, let me, it's always hard to adjust this font. Okay, that's fine. So what does this series here almost look like? The series almost looks like what series?
A geometric one?
That's right. That's right, Clay. It almost looks like 1 over 2 to the nth power. Almost. Got to be a little careful. This is, I mean, it isn't quite like that. I got to be a little careful. That's probably overstating. But I guess what I want to say is that when n is large, for large n values, 1 over 2n minus 1 would be approximately equal to 1 over 2 to the nth power. So this might make us think to use a comparison test with the series n equals 1 to infinity of 1 over 2 to the nth power. Now let's try it. I'm going to go to the next page, and I have the solution very nicely written out here. Let's see if this works. So whenever we try the comparison test, we take a series that appears to be not like exactly like one of the series we've seen, but we want to compare it. We want to compare it to a series that we know something about. So the series from n equals 1 to infinity of 1 over 2 to the nth power, that's a convergent geometric series, right? So the an term, right, is 1 divided by 2 to the nth power minus 1. The bn term is 1 over 2 to the nth power. Okay. And we note here we note that the terms of our series are greater than the terms of that geometric series, because the denominator 2n minus 1 is smaller than the denominator of the denominator of 2 to the nth power minus 1 is smaller than the denominator of 2 to the nth power. Okay.
Professor?
Yes, yes.
So for 1 over 2 to the power of n, how do we know it converges? Or do we use the tools we use for geometric series?
Well, this is a geometric series here. What's the common ratio? This is a geometric series.
Yeah, 1 over 2.
Right. Common ratio is 1 over 2, which is less than 1. So it converges. That's a convergent geometric series.
Oh, I see.
Right. See, we compare the ugly series that we have to a series that we can work with. We make a comparison, you see. But the problem is here is that because I mean, let me just I'll write this in the corner. It's worth writing. The maybe I don't need to do that. The fact is that because of this relationship, the series that we're interested in, okay, is greater than the convergent geometric series. But the fact that the geometric series converges and has a finite sum doesn't tell us anything about the sum of the larger series. The sum could be finite, but it could also be infinity. So comparison test does not work here. The comparison test will not work. It does not work here. Because the sums are going the wrong way, so to speak. If a smaller series, if your series is larger, if our series is larger than a convergent series, then that doesn't mean our series is going to converge. If our series is smaller than a convergent series, then we can say our series converges. But nevertheless, in our minds, we intuitively know that our series will behave like a geometric series as n gets large. Okay, because as n gets large, this minus 1 here, is not going to affect the values hardly at all. So instead of using a comparison test, we're going to try to use what's called a limit comparison test. Okay, a limit comparison test. And let me see here. Maybe I can bring that up in the book here. Let me get that. One moment. What I'm doing is I'm going into section 8.3 in the ebook, and I'm looking at this. I'm going to show you this, show you several things here. So let me go in the ebook. So this is the comparison test, and we try to use part A of the comparison test, but it won't work. It won't work because our series is larger than the convergent series. Okay. So let us look at another test called the limit comparison test. It's actually a beautiful test. It says, suppose that you have two series with positive terms, and you look at the ratio of the terms of those two series, and the ratio as n goes to infinity of the terms of the series, of the two series, is equal to a constant in the limit, where c is some finite number. Then both series either converge or diverge. So what this means, what this really means is when you if the terms of the two series are in proportion to each other in the limit, then the behavior of one series will be the same as the behavior of the other series. That's what it means. Okay, so let's see how this applies to the problem we're looking at. Let me go back to the problem we're looking at. Okay, so we're looking at part A. Okay, and we saw that the comparison test won't work. So let's look at the limit comparison. So since the comparison test did not work, we're going to use the limit comparison test. And what we do is we let a sub n equal the 1 divided by 2 to the nth power minus 1, and the b sub n will be just 1 over 2 to the nth power. So what we're doing here is we're saying, really what we're saying is what we're saying in simple terms, and I'll write it here. Hold on. What we're saying in simple terms is the series that I'm interested in is it like the geometric series as n gets large? That's really what you're doing. That's really what you're doing. So I'm trying to think of a analogy here, but let's just so okay, we're going to apply the limit comparison test. I take the limit of the ratio of the terms of the series that I have here. So that's 1 over 2n minus 1, all divided by 1 over 2 to the nth power. What I do is I multiply, I can multiply by the reciprocal of the denominator, but you could just multiply top and the bottom by 2 to the nth power. And then you will get what you have here. The limit as n goes to infinity of 2 to the nth power divided by 2 to the nth power minus 1. But now what we can do is we can multiply the top and the bottom by 1 over 2 to the power. We want to determine the limit. We do a little algebra on it so that we can more easily figure out the limit.
Professor?
And that gets us to here. Yes.
Can you explain why do we multiply with 1 over 2 to the n power? I don't get that part.
Well, what I want to do is I want to, as n goes to infinity, I have two terms here, one in the numerator that goes to infinity and one in the denominator that goes to infinity. What's infinity over infinity? It's an indeterminate form, right?
Yes.
indeterminate form. So I want to just rewrite the expression so I can determine the limit. And by multiplying by 1 over 2 to the nth power on the top and the bottom, okay, I wind up with the limit as n goes to infinity of 1 divided by 1 minus 1 over 2 nth power. And that's much easier to analyze, right? Because as n goes to infinity, what does 1 over 2 to the nth power go to? It goes to
Infinity.
0, right? 2 to the nth power in the denominator gets big with n, right? 2 times 2 times 2 times 2 times 2. If you keep doing that, you're going to get a huge number. So 1 over that huge number that's going to approach 0. So you end up with getting a limit of 1. And so we can utilize the limit comparison test, because it tells us that indeed, let me just hold on here. Make this a little, there we go. It tells us that indeed that our series is like that geometric series as n gets large. As a matter of fact, because the ratio is 1, the terms are essentially equal between the two series as you go out towards infinity. If you look at the values of the terms of both series, they're essentially going to be the same. So the behavior of the geometric series, the behavior of our series would resemble the behavior of the geometric series. And so therefore, since that geometric series converges, the series n equals 1 to infinity of 1 over 2 to the nth power, that geometric series converges. So therefore, our series has to converge as well. And basically, I have it written out nicely here. Eventually, the two series are very similar. They're very similar in nature. Okay. And so the fact that one series converges means the other series will converge as well. So we've proven that our series converges. Do you see how that works, Clea?
Yes.
Okay, good, good. This was an example. It's actually a very famous example where you know, the comparison test, I think like most of you, if that were on a test or on your homework, you would try the comparison test for this problem, but it doesn't apply. So you have to use, well, another test, and it turns out the limit comparison test does the trick. It works pretty well. Fairly intuitive. Okay, let me give you a moment here to, are there any questions? Are there any questions at all? All right, well then let's go to the other one. The second series here, series B. What's missing in series B? That would be nice to have.
A summation formula, like.
That's right. That's right. An equation and a summation formula. That's right. Well, can we think of one? That's
Yes.
right, Claire. That's right, Jonathan. Let me see here. Let me just blow this up a little bit on my screen. So if we were to come up with a formula here, it's going to be 1 over something. So, you know, you have 1 over 1 there. 1 is 1 over 1. So the terms you have on the bottom, you have 1, 3, 5, 7, 9. They're odd terms. So what would the formula be? What do you think?
2n minus 1.
That's right. That's right, Clay. Good. That's right. 1 over 2n minus 1. Now let me ask you, as n gets large, does this -1 here affect the value of the terms much?
No.
Not really. So you really could try to make a comparison between the series 1 over 2n. But again, the comparison test is, let's try to use the limit comparison test. So let's go to the solution here. So we come up with the formula. There it is, a formula for the series. And we're going to use the limit comparison test. This time, A sub n will be 1 over 2n minus 1. And B sub n is going to be, I'm just going to have it be 1 over n. Okay. Take a moment to copy that. Jonathan, I could have used 1 over 2n, but I know something about this series. What kind of series is the series n equals 1 to infinity of 1 over n? What kind of series is that called?
Geometric?
Well, not yet. It is a p series. It's a p series with p equals 1. But there's also a special name. So that series is going to diverge. That's good. It is a p series, right? It diverges. But this is also a what? Remember the name? Right, harmonic series. Now look at what I'm going to do. Look at what I'm going to do. I'm going to take the terms of the series, of my series, of our series, and divide it by the terms of a harmonic series. Okay, and I guess we can put in a few details here. This would be the limit as n goes to infinity of 1 over 2n minus 1 times n over 1. And that gets us here. And again, we have an indeterminate form. The limit as n goes to infinity of n over 2n minus 1. So, but we could use L'Hopital on it, L'Hopital's rule, or we could just multiply top and bottom by 1 over n. And if we do so, we'll get this result here. And as n gets large, we know that 1 over n approaches 0. So we're going to get 1 over 2 minus 0, and that equals a half. So the terms of our series are basically going to, and for when n is large, the terms of our series are going to behave like 1/2 times the terms of the harmonic series. I have that written on the next page, but let me give you a moment to see if you have any questions here. All right, folks are good. All right, let me go to the next page then to summarize then everything. So our series, I mean, what I'm trying to do here, like, I'm trying to sort of give you an intuitive feel for these tests and what they do. So our series here, our series eventually behaves like 1/2 times the harmonic series, because the ratio of the terms of our series to the harmonic series was equal to 1/2. So, but 1/2 times infinity is still infinity, you see? So our series diverges just like the harmonic series does. If you have a bad apple, okay, an apple that's bad all the way through, well, 1/2 of the apple is going to be bad also. It's like you can't get the bad out of the apple, so to speak. If since the harmonic series diverges, our series diverges too. Now it'll go to infinity about 1/2 as well. It'll go to infinity, just not as quickly, but it'll get there. How many think this is sort of cool, what you're learning today? Kind of cool. Okay, Yonatan's liking it. And Gabriel likes it. How many are thinking, man, I haven't had to do any integrals lately. So, how many are kind of liking that? It's a little something different. Okay, Victoria likes that. And Clea does. Well, I have to tell you, let me see here. Hold on. Well, if you were to, so Jonathan's trying to see, he's trying to get comfortable with this statement here. The way I guess I would think of it real quickly in a nutshell is, hold that thought, in a nutshell is, if you were to, let me see here, let me just bring up the whiteboard so you can, let me show you this. I assume we were all good there. I mean, so if you had this series here, you could write that series like that, and then bring the 1/2 out front. So you'd have 1/2 times a divergent series, and that's going to equal infinity. Now the series we have is a little different, right? Because we have 1 over 2n minus 1. But this will, I want to say it's the right way. It's like if we did this, if we wrote the, let's say we took the series, maybe I can do it like this. Let's say we took the series and split the series up into the sum n equals 1 to 1 billion plus n equals 1,000,000,001 to infinity of 1 over 2n minus 1. This part here, would you agree that would be approximately equal to let me put it down here. This here would be approximately, so if we look at the series, right, as like, forget the first billion terms of the series, but look at the terms of the series starting with the billion in first term. Would we agree that this series is approximately equal to the series 1 over 2n? Does that make sense? All right, well, this series diverges. That diverges. Good, Jonathan. So that means this diverges. You see? And so the series diverges. The whole series diverges. That's really what the idea. The limit test, well, the limit test is in order to say that the limit test just says that the terms of your series are in proportion, they're a multiple of the terms of another series that you know about. You see, there are multiples. So if your series behaves like a multiple of a convergent series, if the terms of your series are essentially multiples of the terms of a convergent series when n is large, your series and that series converges, then your series is going to converge, because a multiple of a convergent series is a convergent series. Well, yeah, and when you do these problems, I'm going to be very flexible when you do these problems, like for your exam, how you establish if the series converges or diverges. There's different ways there's different, students are different in how they explain the concepts, but all the concepts, like students might explain why a series converges or diverges in sort of using different words, or how many kind of like this kind of thinking, what I'm showing you here? How many kind of like this? Maybe this makes things a little clearer. Yeah, Susanna, so see, Susanna, I'm reaching Susanna with this kind of thinking. So I want you to see the different kinds of thinking so that you can intuitively understand these different types of convergence tests that are in the book. In the solution for this problem, what we did was we used the limit comparison test and got a half. And all that's saying is that our series, the terms of our series, are going to basically be equal to 1/2 the terms of a divergent geometric series as the terms in the series as we go out further into the series. And therefore, since the harmonic series diverges, our series has to diverge. It's basically the same kind of thing. Different ways to explain things. And I know that you were kind of happy you hadn't seen integrals, but section 8.3 is called the integral and comparison tests. So I got to show you the integral test now. I'm going to have to show you that. So let me go here and show you the integral test, and then we'll be able to take a break. I'll do example 1 from the textbook. Let me just bring up the textbook here. Hold on, class. So example 1, forgive me, it's here somewhere. Yeah, this is called the integral test. So the integral test says, suppose you have a function that has, the terms are positive, or the function is positive and it's decreasing, then the corresponding, and if the a sub n, the nth term of the series, can be written as the function evaluated at n, then the series a sub n is convergent if and only if the improper integral is convergent. An absolutely fascinating result. An absolutely fascinating result. So let me see if I can maybe, hold on here. Hold on, everybody. Yeah, this time it won't let me blow that up. But basically, if the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. And they note here also that with the integral test, it's not necessary to start the series or the integral at n equals 1. What determines, like here, if you had the series starting at n equals 4 to infinity, you had one of those in your homework, right? Or something like that. that series you could model that with an improper integral starting at 4. You see, a bottom limit of 4. So what is important, and they make another thing too here, another comment that's important. It's not necessary that the function always be decreasing. What's important is that the function ultimately be decreasing. Okay, so let's again, that relates to what happens as the series as you go on to the integral. You know, the divergence or convergence of an improper integral. Well, I don't want to get too much into the weeds here. But here's an example where you really want to use an integral test. So here you have the series where n equals 1 to infinity of the natural log of n divided by n. That would be hard to make a comparison test with. That series, you want to use the integral test. And they establish in the solution that the terms of the series are decreasing. So for the problems you're going to see in the homework, you know, the terms of the series are going to be decreasing or decreasing eventually. Okay, and in this series, they say, well, the terms of the series are decreasing. They show by taking the first derivative that, you know, remember in calculus 1, when can you determine if a function is decreasing? You take the first derivative and see where the first derivative is negative, right? Well, it turns out the first derivative is negative for values of x that are greater than e. And so it follows then that we can apply the integral test. So in other words, eventually the terms of the series are going to decrease. Not the first, you know, 2 terms, but starting with the third term, because 3 is greater than e. You know, e to the first power is 2.718. Eventually the terms of the series are going to decrease. So all you do is now to establish convergence or divergence of the series is, and I'll ungray the box in a moment, but you take the improper integral from 1 to infinity of the log of x divided by x. And then you will establish that that improper integral equals infinity. So that improper integral diverges. And because of that, improper integrals, remember, were section 5.10. Since the improper integral is divergent, then the series diverges also by the integral test. So sometimes students, how many kind of like the integral test? How many think that's kind of a cool test to use?
I have a question.
Yes, Clea.
So when do we know when to use the comparison test or the limit test or the integral test?
Yeah, that comes from training and doing your homework. Most all of the homework problems you'll see in section 8.3 have help aids to them, watch it videos or master it or something. So if for some reason you're a little unsure what to do, you can refer to the help aid and it'll help you. And so after you do section 8.3, you'll have a better intuitive feel for what test to use. Do I use the comparison test or the limit comparison test or the integral test? The integral test you use when it's difficult to use a comparison test or a limit comparison test. And traditionally, you always want to see if the comparison test works. But sometimes you'll try it and it won't work. And then you have to resort to either the limit comparison test or the integral test. And incidentally, remember, these tests are for terms that have series that have positive terms. If you have a series where the terms are alternating, going positive, negative, and so forth, that's called an alternating series. Then you can't directly use these tests. You can maybe do something so you can use them, but these tests that you're learning in section 8.3 are for series that have positive terms. Positive terms only, basically. Okay. Clea, does that help? So you'll get more comfortable with practice. It's like, remember Star Wars with what's her name, Rey, the Jedi. I believe that's her name, right? Rey. Do I have that right? I'm talking the new ones now. I say that because probably the one with Luke Skywalker, you probably don't know that one too well. But how many like Star Wars, have seen Star Wars? Okay, Opiemi, Yonatan has no idea. He's never seen Star Wars. Well, basically, you know, you have, like Rey had to learn how to become a Jedi to fight with her lightsaber, you know, and Luke Skywalker helped her, you know. So that's kind of like what you're doing here with your homework. The homework, I'm the Jedi, right? I'm going to help you, like I'm showing you examples, but then you're going to practice like Rey did, doing the homework and getting better. So you'll be fine. You'll be fine. Are there any other good questions? Yonatan, you have to learn to see Star Wars over the holidays, okay? You won't regret it. You won't regret it. I think David likes it, right? David likes Star Wars, so no, oh my gosh. OPME doesn't like it. Oh my gosh. All right, Yonatan. All right. Very good. Excellent. That sounds good. Okay. Are there any other questions before we? We're going to do more of section 8.3 now. We've talked about the different types of tests of convergence in 8.3, but also we need to talk about how to estimate the sum of a series, right? I mean, it's a natural thing to ask, hey, if a series converges, can we estimate its sum? And the answer is yes. So, but we'll talk about that after our break. So let me stop the recording. Thank you.